I want to talk about yesterday's lab real quick, just to think about what we did. Yesterday's lab was essentially using the scientific method on a hypothesis. That would be the hypothesis that Newton came up with, that the acceleration and net force and mass are related by net force and mass times acceleration. So if we were to put that into the simple fourth step that I want you to memorize, scientific process, what is the first step in that scientific process? Observing something interesting. So we would have to imagine, what Newton might have observed, but step one was observe something interesting. In this case, it's going to be how an object responds to forces. And so then the second step, what's the second step of our scientific method? Hypothesis. Okay, to form a hypothesis, and the hypothesis has to fit three things. What are those three things?
Explain why the observation occurred.
I'm sorry, I don't write nearly as fast as I can talk. Okay, what else do we have?
Based on scientific ideas.
Okay. Based on scientific ideas. And what's the final thing?
Testable predictions.
It has to make testable predictions. And so Newton's hypothesis was that the acceleration depends on the mass, and, well, the last step on the entire last page was basically asking the same question over and over. Well, same two questions over and over again. It was saying, how did acceleration relate to the force? And how did acceleration relate to, okay, that's an A.
Is that fish relate to something?
It means it's proportional to.
The fish means it's proportional.
So basically, Newton came up with his hypothesis, and I don't know what his thinking was, but his hypothesis made these predictions because it was, so these are the testable predictions, because his hypothesis was sum of the forces is mass times acceleration. I know I'm writing it as a non-vector equation here, just making life easy for me. So it makes those predictions, and then what's step three? Test predictions. And so you tested both of these predictions. How did you test both of those predictions?
By adding the little washers.
Okay, you added washers. What did that change?
That changed the force.
That changed the force. And according to Newton's equation, the acceleration, if you double the force, the acceleration should double, because the acceleration, if you just solve that for force, which you ended up getting from going through your work, acceleration is equal to net force over mass. When I put it on anything other than the left side, I like to write force net. Remember, force net and sum of forces are the same thing. So acceleration is force net. So when you doubled the net force, it should have doubled the acceleration. So you tested, and how many people actually measured the acceleration? That is, on the graphs on the left, and the acceleration actually measured the values. You weren't required to, so. Well, in preparation, when I was going over it with the TA, we did all the experiment, and we measured them, and we found that with 4 washers, acceleration was equal to 0.26 meters per second squared. And with 8 washers, acceleration was equal to 0.53 meters per second squared. Those are the actual numbers that we found.
So just almost twice as much for that.
Yeah, I mean, within rounding error, it's exactly twice as much. Now, one test is not conclusive, right? But it passed the first test. Because it's saying, yeah, doubled the force, because you doubled the number of washers, you're doubling the mass, doubling the weight, doubling the force, and it doubled the acceleration. So it passed this test. So that was the first one. The second one, I didn't measure the acceleration for because I was confident at that point. But the second one, what was the second test you did? You added the weight. And what happened to the acceleration when you added the weight? Let's call it a mass. When you add the mass, what happened to the acceleration? It went down. Is that in agreement with acceleration being 1 over m?
Yeah.
Yep. And so the second test, which I don't have numbers for, it passed. Then we finally get to step 4. Did it pass or fail my tests? So what's the next thing I would have to do to continue with the scientific process? I would go back and test not the same, but more predictions or with different types of tests. Because somebody could say, well, sure, in your situation it works, but in this situation it wouldn't. So that's going to be different types of tests, a different situation to test the same prediction or test a different prediction. And when have I proven Newton to be correct? Never. People have done this for hundreds of years in physics labs like yours, tested over and over and over again. So we have really high confidence in Newton's second law because the scientific processes you go through, you develop more and more confidence, but we still haven't proven it right. And one perfect experiment could potentially prove it wrong. Of course, nobody believes that's going to happen because you know what? We've all been brainwashed, right? We've been indoctrinated. But still, we have to be open to, if somebody can come up with an experiment that violates this, then it's wrong. And what would we do if somebody came up with an experiment that showed that the prediction of Newton's second law was not correct? Where would we go in the scientific process method then? We'd have to go back and modify that hypothesis because now we have more information because we know something additional that was wrong, so we can add that in and make a better hypothesis. Now, this is called Newton's law, right? In our hierarchy, we had hypotheses, then theories, then laws and principles. And what makes this a law? Well, it is something that can be written concisely in an equation that's been tested many, many different times in many different ways and has never failed, so that we have high confidence in. So really those two things put together. Okay, now getting on to new material. The topic of the day is momentum and energy. I'm going to try to do the entire chapter here in the next 40 minutes. So let's get started. Momentum. You know I'm a fan of the Oakland Raiders. And we had a lot of momentum going until something happened. What does it mean when you have a lot of momentum going in sports?
You're doing well.
You're doing well. It's going to be hard for somebody to beat you. Now, of course, we did lose to Kansas City twice. But other than that, we were flying until they found a way to break that momentum. Or more accurately, break our quarterback's leg. So momentum, in a sports sense, is it's going to be really hard to stop them. They're on a roll. Much like if you're a fan of... What? I didn't hear what she said. Oh, Patriots, that's what she said? Yes, well. Today is the 15th year anniversary of when I punched a hole in the ceiling of the condominium we were renting on our ski trip. Why? It's also the 15-year anniversary of the NFL completely screwing the Raiders on the, quote, tuck rule. Since you brought up Patriots. Question, Johnson?
No, I was just.
Keep talking.
Okay, I'll keep talking. Okay, so where was I going with all this before she said about momentum? Well, I don't know. Brittany threw me off. We can all give her credit. So when somebody has momentum in sports, it's going to be hard to stop. In physics, it's exactly the same thing. And so this ball coming down at her, even if it was on flat, right? It's not because it's going down slow. It's because the ball is moving. If she was on flat ground and the ball is coming after her, she's going to have a hard time. I always wondered, my son said the same thing, in Indiana Jones and the Temple of Doom, the opening scene, why didn't he just duck and let that ball go ahead of him, right? Wouldn't that make more sense? Except for then maybe he'd be stuck in there. I don't know. Maybe it closed the entrance.
Wait. Never mind. Sorry.
Okay. Or no, maybe it's Raiders of the Lost Ark. I don't know. The first one. It's Raiders of the Lost Ark. Okay.
Wait, if you were to duck, that would solve things?
Well, in that one, there was a track. The ball was coming down, and he's like here, and the ball's coming down here, and he runs out here.
Is that going to show up on our notes?
It will show up on the notes, yes, not on the test. Right.
You should.
But see, if he ducked, the ball goes in front of him. He doesn't have to worry about it having momentum and running over him. Okay, so momentum is really a measurement that has to do with inertia, but it's when something's in motion, right? We tend to think of inertia, it's something that is going to resist change in motion. We tend to think of it as, well, these are stationary here, they have inertia, they resist me starting them in motion. But when something's in motion, it also has inertia, it wants to stay in that motion. And so when we talk about momentum, we're basically talking about how much it wants to stay in its motion. And so momentum is given by the equation. P is the symbol for momentum. P stands for momentum. Why? I have no idea. A lot of symbols I know why, but some I don't. And momentum is measured in just taking the object's mass times its velocity. Momentum is truly a vector, so it has direction. So just taking a simple example, since Casey's up here in the front row with me, if Casey and I were to race to the back of the classroom, and we turned out to, we're not going to. It turned out that we were running exactly the same speed. So we have the same speed, we have the same direction, we have the same velocity. Who has more mass? Me. Okay, it's not that awkward. Okay, I'm more comfortable with it. My wife not as much, but so I have more mass. I have more mass. What does that tell you about the momenta of the two of us? Momenta is plural for momentum. I have more. And what's the practical outcome of that?
It's
going to be harder to stop me. So if we're both running and you're like, well, I got to stop one of these, what's the obvious choice of who to stop? Her. It's going to be a lot easier because she has less momentum. That's what the momentum means. Now, we'll talk about energy in just a little bit, and kinetic energy specifically. That's how much work you're going to have to do to stop. Also related. But it's an easy way to think about the momentum. Basically, which one am I going to have to put more force on to stop? So our first clicker, wow, that's perfectly in focus. There, that's better. When the speed of an object is doubled, what happens to its momentum? By this point, we probably all remember, but it's...
It should just keep us finding it.
Yes, I know it should. It should remember, oh yes, this is your username, this is your password, and these are the channels you usually check. Yeah. It's channel 33 on that one. Yes, it does, you're right. Doesn't have all the high-tech gadgetry. Okay, we have only... 13. According to this, Haley, Jocelyn, Maggie, and Hannah. Okay, now it's just Maggie and Hannah. Hannah, I know you've got this taken care of. Okay, everybody's answered. Woohoo! Perfect. And our answers were pretty darn good here. So because I'm going to run out of time, I'm not going to ask you guys to answer the question unless there's reasonable chance of people misunderstanding. Since momentum is equal to mass times velocity, if you double, in the example I gave with Casey and me, it would be more like doubling or more the mass. And here it would be, changing the speed, doubling the speed. But since it's proportional to both, if you double the speed, you're going to double the momentum. Now, impulse is a word that, frankly, I don't like. Impulse is a term that means the force multiplied by time. Now, if you put a force on something, what's it going to do to that object?
Move it.
It's going to cause it to accelerate. If you put a net force, I should be specific, right? Because it could be that it would be sliding down the hill and you're putting a force to keep it from sliding, right? But if you have a net force on an object, it's going to make it accelerate. And if you take that acceleration and you multiply it by time, remember our definition of acceleration was the change in speed divided by change in time. So if I take acceleration and multiply by the change in time, what's that? Yeah. So acceleration multiplied by change in time is a change in velocity. So force multiplied by time is going to have something to do with the change in velocity. Force is mass times acceleration. So if we get really, really careful, the net force, what we're doing here is saying the impulse and once again, you see they just put force times time, but it's net force times time is equal to mass times acceleration times change in time. It's equal to mass times change in velocity. But if something has a constant mass and changes velocity, what would we call the mass times change in velocity? Mass times velocity has what name? Momentum. So if we throw a change in there, it's going to be the change in momentum. So the impulse is equal to the change in momentum. I guess I should write words out here. The triangle means change in.
Yeah, I forget and then I remember.
So that's why I don't like the word impulse, because the word impulse is equivalent in meaning to change in momentum. When we use the word impulse in physics, we mean we're looking at the net force multiplied by the time over which it acts. Now, this is a real handy idea because notice you can get the same impulse with a bigger force in a smaller time or a smaller force in a bigger time. So something like you're driving along in your automobile and you hit a brick wall. You're going to have a change in momentum, will you not? I was going to show you a little video from, I think it was Moz Australia about this, but they used incorrect physics, and so I couldn't show it because I can't say, okay, ignore all the bad physics. You would have momentum, you have your inertia, you want to stay going, but you hit that wall and you got to stop. There's a certain impulse that you're going to have to go through, your change in momentum. And if you apply a small force, what's going to have to be the time for you to stop? That's going to be a small force. A long time. If it's a large force, what's the time to stop going to be? Short. Now, of course, what really governs things is more about the time. If you have a short time to stop, it's going to have to be a very large force. A long time to stop is going to be a smaller force. Which one do you suppose feels better?
Longer one?
Okay, the longer one with the smaller force is going to feel better. It's going to do less damage to your body. So when our cars do things like crash into stuff, we have things that we wear or things built into our car to try to make it take longer for our bodies to come to a stop. The car's going to stop real quick. Nothing we can do about that for the most part. We do have crumple zones in the car. That helps the car to stop more slowly, which means less force, less damage to you. So there's actually safety things in those crumple zones. Also, you want it to crumple up there and not crumple in like the passenger compartment. Kind of like to keep the space there for your body. So that's another reason for crumple zones into cars. So here's some examples. A truck hitting hay, the hay is not going to supply a very big force. And so it takes a long time for the hay to stop the truck. Of course, anyone who's worked with hay actually knows if you get a big stack like that, it's pretty heavy. It's not like, oh, get it out of the way. And so it probably would stop the truck, and probably before it got that far through it. But when the truck hits the wall, there is no give. It stops instantly almost. And so the force is immense. Everybody understand that concept? So let's talk about safety in our cars. Back in like my dad's day, safety was really not part of the equation. I mean, my dad and his brothers, mostly his older brothers, they got themselves an old Model T, and they decided it's a lot more cool to sit in the back seat and drive than to be up there in the front seat. And so they welded a pipe on the steering shaft, and they welded extensions onto the pedal so they could sit in the back seat, take out the front seat, and drive from the back seat. Also, it made it a lot more fun when you were, doing donuts. Safety, not an issue. Well, as speeds went higher and we started having people die in automobile accidents, we started worrying about safety. So we put safety things into the cars. What should our goal be in our safety features we're putting in the cars? I mean, we want to keep people safe. That's a given. So what are they going to do in physics terms? What are our goals in physics terms?
Maybe a longer time.
Okay, longer time. So what's the first thing they put in cars for safety features? What do you think? You may not know. Seatbelts, lap belts to be specific. So the lap belt makes it so instead of you just fly forward freely until you hit the dashboard, that you have that lap belt that you got a little bit of give, more give there than when you hit the dashboard. But there's a real problem with the lap belt because it keeps your waist from moving. What happens to the melon? Yeah. You go, woo, and your head hits.
Should we drive with helmets?
If you wear only a lap belt, a helmet would be a good idea. Because it just makes it so you're more prone to head injury. And so they smartened up right quick and they added a second piece, the shoulder strap. And that shoulder strap, of course, keeps your head from flying forward. Now, what are drawbacks to these two devices, the lap belt and shoulder strap? Okay, they choke you. Sometimes I will be a bad person and like stick it under my shoulder so it doesn't choke me, right? And a lot of cars have things so you can adjust the height to make it so it's not so bad on your neck.
Haven't some of them like killed people in accidents?
I'm sure they have. I don't know of any examples.
Not like the seatbelts really.
But, they will, like a seatbelt, will really hurt you. A shoulder strap, if you, crash hard, it's going to put a lot of stress there and you'll get some bad bruising. You break a rib or something. So they said, well, let's make this a little safer. And so these days, except for the Yugo, okay, you guys were born after the Yugo died, but Yugoslavia wanted to produce a car. And they came up with the grand idea of a one-size-fits-all. They didn't have any of that namby-pamby, you can slide the seat forward and backward. Who needs that? Just adjust your legs, put your knees high if you're tall. Anyway, they also just bolted the seat belts to the chassis of the car, which is what they used to do, which means there's no give. Most cars these days, you have a spring system. So if you pull against that, well, first of all, to make it so you don't have to have it snug all the time. It's got the little move with you, unless there's a big acceleration. There's big acceleration, it locks. But then you have that spring back there that pulls against you, so it extends the time for you to pull against it before you get to its limit. Extending the time, what does that mean for force? You have the same impulse because you have the same change in momentum. But if you extend the time, what is that doing to the force?
Makes it smaller.
Makes it smaller. So you're going to have less damage done by the belt because it just takes longer. But then they got really complicated and they put in airbags. What's the purpose of an airbag in an automobile?
To protect yourself.
Okay. to protect you. How does it protect you?
It gives you website. It doesn't. It keeps you from hitting the dash. From flying out.
Keeps you from hitting the dash. Like everything else in our car safety, its goal is basically make you stop slower. And so how does it make you stop, or extend the time? How does it do that? When it detects that your car has had a collision, which according to internet videos could be if an old lady you're honking your horn at hits your bumper with her purse. I don't know if you guys seen that. You have an explosive, and that explosive causes a rapid expansion of air and blows a balloon out at you. And the balloon has big holes in the back so that it will immediately deflate. But how fast is that balloon deploy toward you? 200 miles an hour or so.
That's why it hurts.
Yeah, that's why it hurts. If you're short, it can actually be a safety issue because you want it to have reached its full expansion before you hit it, not to be coming out and you hit it when it's coming out at 200 miles an hour. So they're actually, I believe it's a nationwide law. If you're really short, and I doubt anyone here is in that situation, you can actually go to the dealership and tell them to turn off the airbags, the front airbags, because it's more danger than protection. Because you don't want to get hit while it's coming out.
Do you know what height that is?
I don't.
I think it's like, I want to say it's under 4 foot.
Oh, that's
The kids under 4 foot aren't supposed to ride in the front seat. Well, that's actually in my truck. I can literally put the ignition key in on a slot in the dash and turn off the passenger side airbag. So if my kid had to ride in the front.
Mine's just a push button. It also has a weight sensor. If the weight's below a certain level, it won't turn on. Anyway, so the airbag deploys very quickly, and then it deflates pretty quickly because it's just got big holes in the back. But the idea is you hit that coming forward, and you're pushing on it, but it's pushing back and deflating, so it's going to take maybe a half second instead of 1/100 of a second. If you go from 1/100 of a second to a half second, that's 20 times longer, hence 1/20th the force. And that will really help you survive a crash. And so, I got some pictures here just to give us the idea. All of these things are dealing with that whole momentum-impulse relationship. You had momentum, it's going to change, means you have to have a force acting over time. And if we go back to, well, actually, I wrote it on this. If we go back to this equation right here gives us a new way of writing Newton's second law. The new way of writing Newton's second law is that the net force, which is mass times acceleration, that was our old way, is equal to mass times change in velocity over change in time, which is change in momentum over change in time. I say this is a new way. That's actually the original way. Newton's second law is really the net force is equal to, well, it's a calculus equation. It's really this. Net force vector is equal to, the D's mean change in as well. And so it's change in momentum over change in time is really what Newton's second law is. But you guys don't know calculus, so we never show it to you that way because we don't want to confuse you. Okay, I just showed it to you. Let's write it this way so it doesn't have the confusion factor. Okay, now second clicker question. A fast-moving car hitting a haystack or hitting a cement wall produces vastly different results. Both experience. So assume it's the same car and the same speed. So same mass, same speed. It hits the two things. Which of these answers is correct? Do they have the same change in momentum, the same impulse, the same force, both A and B, or both all of A, B, and C? Waiting for one. Okay. So our answers are now all over the place. 2, 5, 4. Something I can't read in 1. By process of elimination.
I think it's 6.
So we did not have a lot of agreement here. So turn to your neighbor. Talk it over.
Okay, what's that?
But I figured stop a lot faster than if you did.
What'd you bet?
I probably.
I was thinking it's 8.
Would stop overall. Versus when you're hitting a wall, so if you're hitting a wall, you would probably slam it down. But if you hit like a haystack, makes sense in my brain. You might just have to, like it's stop overall, but everything's one way versus if you hit a wall, right? Right. One I don't have an opinion.
Yes, you do. You have many thoughts. Okay, let's go ahead and answer it again now you've discussed it.
It's like the same force in a short amount of time.
Okay. Jocelyn? We're entering again after you discuss it. See, I want to make sure people get their credit.
Thank you.
Okay, this time we had same 3 down, 1 down, 1 down. Go ahead, just tell me what it is so I don't have to
11.
do any thinking. Okay, now let's go to Skyla for a clear description.
Okay, so I wasn't like 100% sure, but like since they're both with the momentum, it's like so both like the mass and the velocity is the same for both like before as it hits both, and then the impulse, since it's the change in momentum, they're both like the momentum is both changing.
And so you answered?
Oh, A and B.
Okay, so you answered D. And she's absolutely right.
Yay.
Right, your momentum initial is the mass times the speed initial. The subscript I just means to start. And since they start with the same speed and have the same mass, they have the same initial momentum. Well, when it comes to rest, what's the final speed going to be? And so they both have the same change in momentum because they start with the same MV and they end at 0. So A had to be true. But then we have the definition that change in momentum means the same thing as impulse. And so since these words mean exactly the same thing, if one's true, the other has to be true. Now, what's going to be the comparison of the forces?
The cement walls exert more force against the object than the haystack.
Right. The cement wall is going to exert more force. That's why it stops it more quickly. So it couldn't have been that one. And so that left us with this. Yes, Tiffany? That's true.
Well, wouldn't the force change because of the objects in the city?
Yes. As we just said, the force is going to be different, not the same.
You could just blow over a haystack sometimes.
The force and the time, right? The definition of impulse is equal to the change in momentum. and the impulse is force multiplied by the change in time, means that while we have the same impulse, if it's going to stop you quickly, then the force is going to have to be high, so force multiplied by time is still the change in momentum. If it stops you slowly, then the force is going to be much lower because you have a larger time. And so those all tie together. But impulse is not only force multiplied by change in time, it's also equal change in momentum. And I appreciate you asking questions because that's the reason I do these things, is to make sure people understand. And if you're just like, I clearly don't understand this, well, then what's the value to you? Now, conservation of momentum. We saw that according to Newton's second law, the net force is equal to the change in momentum divided by change in time. So that means if I solve that for change in momentum, I'll just multiply change in time by both sides, on both sides. I'd have change in momentum is equal to net force multiplied by change in time, which we also call the impulse. Now let's take my example of a ball. If I let go of the ball, will it have a change in momentum?
Yes.
Yes. Why does it have a change in momentum?
External force of gravity.
There's the external force of gravity. The net force in the ball is the force of gravity. And so if I take that force of gravity acting over time delta t, I'm going to have an impulse of force of gravity, mg, multiplied by that time. Why does it not have a change in momentum right now?
Zero next to it.
Because I'm applying an upward force so that the net force is zero. And because the net force is zero, there's no change in momentum. In physics, the word conserved, and actually this is pretty much universal, means it doesn't change. You have the same amount. And so in the situation where the net force is zero, then we say momentum is conserved. It doesn't change. Now there's another option there, because change in momentum is net force multiplied by change in time. So also if we have no time pass, momentum is going to be conserved, which if you think about it long enough becomes really obvious. If you have no time pass. Yeah, it's not really possible, right? But if the time is very, very short and the force is not enormous, it's still approximately zero. And so that's what we use. When we have car collisions, one car hits another. Before the collision, we had, brakes and friction, and we definitely wouldn't say the momentum was conserved. Yeah, I got something on my plate. It's been on there for since Christmas time. That sound. It's not coming off apparently. During the collision, when you have the two cars hitting each other, the actual time for the change in momentum because of the collision is very, very short. And so the force of friction external to the two cars is small compared to the force between the cars. It's small compared to the time. And so it turns out that we say during the collision, and only during the collision, momentum is conserved. After the collision, once again, momentum is not conserved. So when there's an accident, when I was teaching at PUC, I was part of the Angwin ambulance and Angwin fire boat. And so we had to respond to accidents. And as soon as the law enforcement people come, they get out their little wheel and they start measuring the lengths of skid marks. Why do you suppose they're measuring the lengths of skid marks?
See what the speed was when cars actually collided.
They're going to figure out how much, you know what the force is, basically the force of friction, right? Because if you know the mass of the car and you know rubber versus asphalt or rubber versus concrete, you can calculate how big the force is. And then if you measure the distance and you know the mass of the car, you can have the acceleration and the distance. And from those, you can find how much the speed has changed. So they're measuring all those skid marks, and they know when everything stopped. It stopped here. It skidded this far, calculate how fast it was going when it started that. And then before the collision, you had these. And they're going through those calculations so they can calculate exactly how fast the cars were going to see, was car A speeding, was car B speeding, or what happened. Other systems where momentum is conserved. Here's a real-life example. I took my then-girlfriend, Nalco, to Riverfront Park in Spokane. They have an ice arena there. And I was like, this is going to be cool. And so I explained to her, okay, so we're standing on ice skates. There's me. Naoko's kind of short. And I said, okay, now I'm going to push on you. And because we're on ice and we're going to have our ice skates straight, we're going to have virtually no friction. And so the external forces on us in the horizontal direction is going to be 0 if we consider the two of us as our system. And so when I push on her, there's going to be a force acting on her that's going to make her accelerate. A force acting on me, the same force. Newton's third law says if I push on her, she's pushing back on me with the same force, making me accelerate the other direction. But because of our different masses, she's going to accelerate more, she's going to go faster, and I'm going to go slower. This is going to be totally cool. It's a total good physics demonstration. Yes. Yes, she did. And she got really angry. It turns out this isn't a good physics demonstration. But it seemed good at the time. So here's the way it was supposed to work. Momentum initial was 0 because we started stationary, right? That's mass of Richard times speed of Richard initial plus mass of Naoko times speed of Naoko initial. And both of the speeds were 0. So we started with that momentum. Now, during the push, each of us has a change in momentum, but the net force, the external forces acting on us was 0. So force net equals 0. Therefore, change in momentum equals force net delta t equals 0. So momentum final has to equal momentum initial equals 0. But that's equal to the mass of Richard times speed of Richard, or velocity of Richard final, plus mass of Naoko times velocity of Naoko final. Now, for good approximations, let's just say that our masses were, well, let's be realistic. Mass of Naoko, at least at that time, was about 40 kilograms. I told you she was small. Mass of Richard at that time, not as big as the mass of Richard now. It was probably around 90 kilograms. I'm trying to be honest. And so if we take these, we can say, let's suppose that the speed of Richard final is equal to 2 meters per second. What's the speed of Naoko final going to be? Well, we can just do the calculation. We have the mass of Richard times the speed of Richard final plus the mass of Naoko times the speed of Naoko final is equal to 0. So if I just solve that, I'm going to have speed of Naoko final times mass of Naoko equals speed of Richard final times the mass of Richard minus sign. If I'm going to move it across, I have to subtract. And so there's a minus sign there. Divide both sides by the mass of Naoko. And I get this, I'm at the bottom of the page, sorry. Speed of Naoko final should be equal to minus my speed of 2 meters per second times my mass of 90 kilograms divided by her mass of 40 kilograms. And so 90 times 2 is 180 divided by 40. I should be able to do this better. I sometimes feel like an idiot when I don't do my math easily. Minus 4.5 meters per second. It was easy. And so she should have been going a little bit more than twice as fast as me. What does the minus sign mean? Opposite direction. That's how it should have happened. As you already figured out, she fell, she cried, it was a bad date. Then I took off my skate, and my sock was just soaked in blood. I was like, oh no, I must have had a blister that burst. So I take my sock off. No, my foot was pristine. The previous user of those skates had a blister that burst. Yeah, it was a great day.
Did you get your money back?
I didn't ask for my money back.
It was. Did she just fall because she was clumsy? Like what was the?
I don't really have an answer for that.
She was supposed
We
to just
discussed
go on
it.
really fast and then if somebody-
Yeah. Anyway, let's not go over the reasons here because they'll probably end up pointing fingers at me. Now we have collisions. Collisions between things. We've just been talking about collisions, right? Collisions between cars. Well, when we have collisions, we break them into two fundamental types. Elastic collisions are collisions where they bounce off of each other with no deformation. Ideally, this bouncing ball would be an elastic collision because it comes right back to the same shape and size. But elastic collisions are also supposed to return all of the energy, the topic that comes next. This ball clearly doesn't. It absorbs a lot of energy. So we have to talk about that before it makes a lot of sense. In elastic collisions, the two items stick together. In both cases, if it's a fast collision, the momentum is going to be conserved. So in our lab next week, I haven't actually looked to find, but they've got to have one for collisions. That's probably what we'll do in lab next week, where we'll be looking at the collisions and comparing the energy and momentum of these different types of collisions. So here's some pictures just showing collisions. This is a first collision, a moving green ball, a stationary yellow ball. They hit each other. The green ball stopped, the yellow ball moved. What type of collision is it going to be if they bounce off of each other? Elastic. And in our simplified world, all collisions will either be perfectly elastic or stick together. In the real world, there's things in between. They're always in between. Well, this never occurs in real life. Here we had two coming toward each other. They bounce off each other, go back. And here they're both moving the same direction. Those are examples of elastic collisions sticking together like these two carts in elastic collision. Now, I totally didn't get as far as I wanted. Work and energy is our last topic. We're clearly not going to play with the bowling ball and swing it back and forth today. I'll probably do it in the class next week because it's just fun. Work, well, we all know what work is. I'm working right now, right? I'm up here earning my money by yammering at you. But in physics, we have mechanical work. And mechanical work is a special type of work. Mechanical work is a force on an object with motion parallel to that force. So if I take as an example, we're not supposed to have any food or drink. If I take this non-drink and I push on it and it moves, that's doing work because there's a force in the same direction I'm pushing. If I push on the table's not moving, hence no work. So we have an equation for that. The work is the force times the distance, but it has to be parallel. You have to have force times distance parallel. And you might ask, well, what does that really mean? If I have this ball, what direction is the force I'm putting on the ball right now? Up. If I walk like this, it has a velocity, but that velocity is perpendicular to the force. So I'm doing no work on it if I'm moving at a constant speed because the force is up and the velocity is horizontal. For work, it has to be the same direction. So in the example I had, like second class here, I think, Casey and me pushing on a car, and I'm pushing and she's pushing, and if we're both pushing really hard and it doesn't move, how much work am I doing? How much work is Casey doing? None. Now, what if I push harder than Casey? Because I'm pretty sure I can. I'm heavier, right? So I can get more friction, probably stronger too. Good guess. So if I'm pushing harder and it moves toward Casey, now we have my force, big force, the distance it moved, I did work. What about Casey? Casey would actually have a negative work because her force is the opposite direction of the motion. That negative work means she's taking energy out of it. My positive work means I'm putting energy into it. And so I've got to cover energy. It's so important in everything we're covering this class. So I'll pick up with energy beginning next class period.